Um, okay, before I get started, there is this event going on, Expo IT Product Suppliers. It's happening on Tuesday, the 25th, in Minneapolis Convention Center, the ballrooms A and B. There are 2 shifts, looking for volunteers to start, check in people coming in and other, I don't know, volunteer kind of things. But it's good to be there. It's nice interaction. You meet industry folks. So if you're able and willing to volunteer, you may contact Billy, the FSCN Club president, and that's his email.
I think Minnesota IT is reimbursing student parking. So if you have to pay to park down at the convention center, that's what the finalist was the reimbursing for that. Yeah. You just stay in your receipt.
Awesome. Okay, so I have few slides on atomic absorption. I'll finish that and go into IR. On Friday, Ted will start the moisture lectures. What I want to do, since I want to make sure that the IR lecture is completed before Friday, because it's part of the exam on Monday, you'll see that I'm going to zoom through some information and slow down on other information. So with that, you will know which is important and which is FYI kind of deal. All right, so, because I have to finish lecture and make sure that I go over the things that I want you to know about the IR. All right, so just to wrap up AA, I just wanted to give you chances to earn some points participation and get us going to finish the lecture. So what's the difference between AA spectroscopy and AES spectroscopy? Okay, all of you have done the atomic absorption lab, and we had the lecture last.
AES absorption spectroscopy, AES emission spectroscopy.
Oh, okay, but how are they different?
It absorbs the light energy from the ground state and excites, and emission is when it comes from the excited state to the ground state, it emits fluorescence.
It will fluoresce, and that's what you absorb, measure. I mean, you measure the emitted light as the atom goes from excited state to ground state. In atomic absorption, you actually measure how much energy the atom absorbs. So what are the sources of excitation, or the source of excitation for AA versus ICP? What gets the atom S?
Is it heat and plasma?
Huh?
The AES use heat as the source and plasma for AES.
You're right about plasma, inductively coupled plasma. The plasma atomize and excite. In AA, the flame atomize. What causes the excitation of the, the lamp? You have a lamp, the source of the energy, that in it you have a cathode made up of the metallic form of the element that you are detecting. So it will emit radiation in the spectra that is specific for that element. So in the AA you have a hollow cathode lamp. In the ICP, the plasma is the source of atomization and excitation. What's the type of energy absorbed by the atoms when they are hit by light energy?
This kind of the atomic state of the molecule, the way shares different
So, yeah, in the atomic state, what kind of energy does the atom absorb? You know, remember there's 3 different types of energies. What's the form that is absorbed by the atom? Yes, Sarah? Electronic. Okay, so if you have an atom, and that's what we are measuring absorption of atoms, the only energy that we'll be measuring is the electronic energy. If it was a molecule, there could be electronic energy, could be vibrational energy, and could be rotational energy. It's very important that you know the different types of energy. You'll see that I'm going to ask this a lot. I already did a couple of times. Okay, how do we get the minerals in solution? Yes?
So the streams use carbon?
And then what do you do to it? You ash it, release it from the carbon, and what did you do in the lab? You added, Sven? Yes. So first of all, Tara was right. You have to ash it to get it out of the carbon method, and then you to solubilize it, bring it back in solution, use concentrated acid, and then you dilute it once it's in solution. Okay, great. So moving on, I was there last time, ashing, dry ashing, and wet ashing, and I'll talk more about them individually when we cover the ash chapter. But the difference is, like I said last time, here you use heat, high heat to combust. Here you use corrosive, highly concentrated acid to combust the carbon matter. Very rarely you do direct injection when you don't have a lot of interference from the carbon matter, and one example is oil. So all of you have done the labs already, so you have noticed that you had a reagent blank and you had a standard blank. The standard blank was prepared in the same solution as your standards, but did not have anything in there. So you used it to just zero the equipment, to tell it that is your 100% transmittance. And then the reagent blank, you prepared your reagent blank the same way you prepared the sample, right? So you had the crucible, it didn't have any ash in there, but you used the same acid, same reagents, same water to bring it to the same concentration as would your sample have. And that to account for any contamination that might come from the reagents or contamination from the water. If the water hasn't been distilled properly, it might have calcium in it. If your reagents are not mineral grade reagents, they might have some mineral in there. And we noticed that with some groups. Some reagents, blanks for certain groups was 0.5, as high as 0.5 absorbance, other had 0.2 for the same mineral element. But because some groups diluted with 10 milliliter HCl, other groups diluted with 1 milliliter HCl, the HCl was not mineral grade HCl. So that's why each group had their own reagent blank to prepare. Standards, obviously we use standard to calibrate and measure absorbance versus concentration and construct your standard curve. And the labware. All of the glassware that you guys worked with, and even the crucibles before the sample was ashed in them, they were acid washed. So all of them, not just washed by soap and distilled water, they were rinsed with dilute acid to make sure that your glassware are not contaminated with minerals. So they were acid washed. So it's very, very important that the utensils that you use for mineral analysis being well cleaned to prevent carryover from utensils. Because even if you have a reagent blank, one tube or one volumetric flask might be more contaminated than another. So you cannot correct for that. You can correct for reagents, but you cannot correct for individual contamination of the glassware. That's why all of them needs to be washed. Okay, usually for calibration, your standards are almost 100% pure. The purest form of the element is what you want to work with. And we want to make sure that our absorbance and concentration is in the linear range. So, because you do not want to measure where you have curving, then that would not be an accurate estimation of your concentration. And you don't want to measure way below the sensitivity of your detector, way below the threshold of that particular detection. So you want to make sure that you work in the area where you are sure that it's a linear relationship and within the threshold of the instrument. So that's why different standards are diluted differently, because every mineral have different linear range. And that's why your samples also, depending on the content of calcium in cheese or the content of iron in whole flour, you had different dilutions so that you are fitting your samples in the standard curve. There are some interferences in atomic absorption which we try to avoid. One is spectral. For example, optimum or maximum absorbance for iron and zinc occurs at the wavelength of 213 nanometer, both of them. But in the lab, do you remember the wavelength you used for iron? Does anybody kind of nerdy remember this? No? 248. It was 248. So we chose another wavelength you have a decent absorption at. So instead of selecting 213, you will have interference from zinc. We selected the less optimal one that you don't have interference though. Okay, background. We talked about in the lab how atomization is really important. And if there are particulate and the flame is cold, for example, did not cause complete atomization, you'll have the molecules in a particulate form in the flame. When the light hits that particle, it's going to scatter the light. And when that happens, then you have an overestimation because less light will reach the detector, less transmitted light will reach the detector, then you overestimate absorption. Transport interference has to do with the nature of the sample, the viscosity of your solution, the density, how would that impact the transfer of molecules and atomization process in the flame. That's why if there is an issue with differences in viscosity or density, you prepare the standard in the same kind of consistency. So you account for that. Volatilization, we talked about that in the lab, the presence of calcium and phosphate, generation of calcium pyrophosphate, large molecule will not be volatilized and hence atomized. So what do we use? Do you remember what you used to prevent that? Lanthanum chloride. The lanthanum will react with your phosphate, preventing it from interacting with the calcium so that that large molecule does not form. The other thing that we also talked about in lab is ionization. So you want to have the optimum flame. So the flame is not too hot, so you don't end up converting your atoms to ions, which will not absorb the same way at that particular wavelength. So you'll have an underestimation if you get ionization. This is just a comparison between AA and ICP. Both measure metal concentration, obviously, in complex matrices, and both have excellent precision and accuracy. So there is no comparison or differentiation between the precision and accuracy of both. The AA advantage, it is, first of all, cheaper instrument to have, and it's old, it's been there for a long, long time, so the kind of the maintenance is known for it, how to handle it is much known than the ICP. The ICP advantage obviously is multiple elements, simultaneous detection of multiple elements, which you cannot do in AA. You always have to stop, change the lamp, and sometimes even if you have multiple lamps in the system, you cannot analyze more than 5 at the same time. So, and the other advantage is you don't worry about ionization because the fact that you don't have ionization when you have plasma, because of the fact that the plasma is already composed of ionized argon gas that prevents the ionization of the atoms. And finally, detection limit is much lower for ICP in nanograms per milliliter compared specifically to flame. If you look at graphite you have even lower detection limit. So if I'm just comparing flame to ICP, ICP has a better detection limit. And another advantage that is not listed here is you can link ICP to mass spectrometry. So you can even reduce the threshold even more by linking it to MS and also having multiple detection at the same time. So with that, that would be the end of AA. Any question on AA before moving to my most favorite lecture in the entire world? Not IR, spectroscopy. Chelsea laughs, she knows it's not my favorite lecture.
Not at all.
Okay, here we go. So like I said, pay attention when I'm slowing down. and you can zone out when I'm going fast. Okay. All right. So infrared spectroscopy. Boy, that's a crowded one. Okay, let's see what we have here. So infrared spectroscopy, the main two regions that we are interested in terms of food analysis, there is the mid-IR region and the near-IR region. So you have the infrared here is below the red, and it is larger in wavelength, so it carries less energy, so it has less frequency. And so they have the near, that means that the shorter or closer to the red, right here, 0.8 to 0.5 micrometer. Notice now the unit is not in nanometer, it's in micrometer, it's larger. And then you have the mid-IR, which is a little bit longer. We are not interested in far IR. So it is mid-IR and near-IR region is what we're interested in. And in there you have different types of detectors. You have the dispersive detectors and the Fourier transform detector. We're going to talk about that. And then the detection is based on two main interactions with light. It is either reflectance or transmittance. So either we're measuring transmittance or we're measuring reflectance for quantification and qualitative detection. So you can do both qualitative detection and quantitative analysis. And yeah. So from what you've heard about IR and food analysis, can you provide some examples for when IR is used? You can provide a specific example, you can provide a general example.
Quantification.
Quantification, okay. That's a very general example for quantification. You can use it for quantification of almost a lot of different compounds. But if you are monitoring something online, what would you monitor it with? Or what would it be? If you're producing and you want a quick measure of something, again?
Dose.
You could, but yeah. I make it less simpler. I mean, not less simpler, more simpler. Moisture, fat, protein, compositional analysis, that is. So quick measure of proximates is another one where you would calibrate the IR instrument using standards that you have analyzed using official methods of analysis, and then you can run quick analysis online. What other? Yes, Misha?
Identification.
Identification. Good. I'm going to spare, because of time, here's what we have. We have qualitative detection. You can, for example, melamine detection in infant formula. They've used IR to do that, so you detect presence of a contaminant. Identification, try to get structural identification based on the absorbance of different bonds in a particular compound. And structure elucidation. For example, Raman spectroscopy is often used for structure elucidation and FTIR as well. So I'm going to give examples on that. Let's see. Quantification, and what I want to say for composition analysis, it's very important that you know the difference when we say primary method of detection and a secondary method of detection. Do you remember that from the very first few lectures in analysis when I said primary methods of detections are what? What kind of methods are primary methods of detection? AOAC methods, AACCI methods, but that means standard methods or official methods of analysis. Secondary methods are those that are based on calibration using primary methods. So IR is a secondary method of analysis for compositional analysis. And we use IR quite a bit for quality assurance and forensics, trying to identify unknowns in our sample. That's IR is a commonly used tool. So the benefits of IR, it's non-invasive. That means it's non-destructive, nothing. You don't even change the structure of your food, and it's very rapid. You get reading very, very quickly, and you really don't need a lot of sample preparation. Oftentimes, you can just put the sample as is. Sometimes you do grinding, especially in near IR. You have to, if it's a solid sample, you would just grind it to homogeneous particle size, and that's about it for sample preparation. It's very suitable and efficient for routine analysis. That's why I say it's very much used for online measurements. So for example, those of you that are working on your projects already and you're trying to identify tests for during processing, and if some of the tests are, let's say, quick test for moisture, or quick test for solid, or quick test for fat, oftentimes it's the IR, not the lengthy oven methods or the lengthy fat analysis methods, for example. Energy efficient, environmentally friendly. You don't need reagents. You don't have any bad outputs that come out of that instrument. So in IR, it's the same principle as absorption and fluorescence spectroscopy. You have a source of light, and then hit your sample. Some of the light gets absorbed, and the remaining light get detected. That's in the case of transmittance. In the case of reflectance, I can show you a picture later on. And the difference, or that the detector will convert transmittance into absorption, and you can get a spectra. You can, in an IR, you can get a spectra based on transmittance, not necessarily absorption. And then with IR, what's beautiful about it, it's always you get a spectra that is specific for that particular structure. Because every structure is made up of different molecular bonds, and each molecular bond has different absorption of light. So you can get very distinctive fingerprint, and that's cool for identification and structure elucidation. So just to remind you from spectroscopy lecture is that you'll have different energy state. For IR absorption, it's equivalent, the energy is equivalent to vibrational energy. So here, you don't have in vibrational energy, the energy that is carried by IR is not enough to cause any electronic energy gain or change in electronic state of the matter. So the energy, the vibrational energy is very minute compared to electronic energy. And like I mentioned earlier, the spacing is quantized, meaning it's not a continuous scale. Every molecule will have different spacing, allowable energy transitions. And this is based on the change in the vibration of the atoms within the molecule. The atoms within a molecule, the bonds are always in a motion, and change in that motion is caused by absorption of IR radiation. So what you are really looking for is a change in a constant motion that is happening at a ground state. Yeah, I mentioned that. And the IR radiation is a measure of its frequency, and we talked about the relationship of energy and frequency. But what's unique about IR spectroscopy is that oftentimes your axis does not have a wavelength. It's reported as wave number. And wave number is 1 over wavelength in centimeters. So that's what you will see on an axis. You see percent transmittance and wave numbers instead of absorption and wavelength. Okay, so like I said, in a covalent bond you have atoms that are in constant motion due to the stretching and bending of the atoms in a bond. And when you apply when they receive energy equivalent to vibrational energy, so they can get stretched. But they don't remain stretched. They will compress again by spring force. So So that you have, and then this is the stretching, and then bending, this would be bending as well. And what causes the stretching and bending is changes in the momentum or dipole moment, change of charge distribution, up when the molecule absorbs radiation in the IR region. So that's this here. And when absorption occurs is that when the frequency matches the allowable energy change, that's when a change in the amplitude of the molecular vibration occurs. That's what I said earlier, is that it's a constant motion, but when the motion amplitude changes, that would be due to an absorption of vibrational energy. Okay, so here what you see is IR in the mid-IR region. So mid-IR region produces nice sharp peaks. And this is a spectrum. Here you have wave number, and then here you have percent transmittance. You can also have another here relation to wavelength, but often you don't see wavelength in micrometer, you just see wave number. And then what you see here is in transmittance. So the peaks are downwards rather than upwards in absorption, because you have 100% transmittance until a bond absorb light, then the amount of light that is transmitted get reduced in that region. So that's why the peaks are downwards, not upwards. And this is a typical spectra of butyraldehyde. And then you'll see that every peak corresponds to a particular bond, a stretching of SH, or a stretch of CH, bound to C is double bond to O. So each, and this is C double O, so each bond within that molecule will have a specific either stretching or bending at a particular wave number. So you get a spectrum for the entire compound, and then you can use library checks to identify, okay, so this looks like butyraldehyde based on previous library inputs. So here's a table in your chapter 23.1. So this is showing the different groups within a compound, and each group, what bonds will be stretching or bending, and at what frequency or wave number you can detect that stretch or bend. So it's just kind of a reference table. IR radiation can be employed for mineral analysis following atomic absorption technique. Who says yes? No one? Who says no? Some of you are undecided. The brave souls that said no are correct. So of course not, because atomic, you don't have a vibration of atoms in a molecule, basically. So no, you don't have IR absorption for atoms. Okay, so instrument, I'm just going to start going a little fast here. In instrument, you have the dispersive instruments, and these are the older models for mid-IR. So in there you have monochromator, that means you have a unit that disperses light, either a prism or a grating agent. So what happens is the light gets dispersed and sequentially, not simultaneously, sequentially pass through the sample, and sequentially you generate a spectra. And the other components is very similar of that instrument is very similar to UV vis detector. And oftentimes it's double beam. If you remember with double beam, that means you have a reference cell and a sample cell, and the light gets split and goes through both and gets corrected. So there are different sources of radiations, different detectors, and the role of the monochromator. So there are old instruments. Like I said, they are available, but not very much used. Now, the most interesting or mostly widely used is the Fourier transform IR. So in these instruments, remember the interference that we talked about earlier, and I told you I'll bring it back for IR. you have mostly interferometer instead of a monochromator in Fourier transfer. What that means is that you have the source of light and it gets split in, there's a beam splitter, and then there are mirrors that are positioned in certain positions that allow constructive or destructive interference of wavelength. You can control, that is, the intensity of the radiation that gets to your sample at a particular wavelength. Okay, so this is very common in Fourier transform IR, so that you can direct your spectrum in the area that you are most interested in. So you can amplify or cancel and get what you, and you can change the location of these mirrors to change the amplification or cancellation. So you don't have a dispersion of light, so you don't have diffraction of light. All the wavelengths arrive at the detector and they're measured simultaneously. So that's the benefit of that compared to the dispersive unit. So all of the light reaches the detector, and there you have very complicated mathematical calculations that convert all of these signals into a spectra. And they call it Fourier transform calculations. So compared to the old instruments, the dispersive instrument, you have faster acquisition of the spectra because of simultaneous detection, and then you have improved signal to noise ratio. So you have transmission IR, attenuated total, and internal reflectance IR. So the transmission is similar to your UV absorption, is you have a sample, and mostly it's liquid, unless it is solid that is ground with potassium bromide and dispersed with nodule, mineral oil. But often it's used for liquid, where the light goes through, and then sample absorbs light, radiation, and the transmitted light gets detected. So that is very common. The one thing that in mid-IR, we cannot use glass or quartz. They absorb mid-IR radiation. So need to use cells with this particular composition that does not absorb mid-IR. The reflectance, these are two reflectance. They have the same principle. One is for solid and one is for liquid sample. And with that, your light hits your sample. Part of it goes in for very small micrometers, and then the light gets reflected. So part of the light got absorbed, and the rest of the light got reflected. So the detector measures the reflected light that wasn't absorbed by your sample. So it's either solid or liquid. That's why it's called either this or that. You can link gas chromatography to FTIR, which is cool, so that you can have a separation with GC for gases. And then as they pass from the column, they can be linked to FTIR, and you can get FTIR detection. So gas chromatography coupled with FTIR. You can have a microscope linked to FTIR, which is also really cool. Here you can do something we call structural mapping. So if you have a piece of, let's say, Cheerio that has crystallization of sugar on it, but the crystallization is not unique and you want to monitor it over storage. So what you would do, you put a slice on here, and then you would look at a particular, you put the light projected in that microscope, and then at a very small size or area of your sample on a microscope, you can get a spectrum. And then you move it, and then you put it on a different position, and then you get a spectrum. So you can see the distribution, for example, of crystallization on that piece. So you call it mapping, kind of mapping, which is pretty cool. All right. If you want to use mid-IR For quantification, then you can apply Beer's law. It's basically same principle as UV or vis, but here you have IR instead of visible or UV light. And what's commonly used are milk analyzers. So there are really common analyzers for determination of composition of milk. And that would be a quick, like when they receive the milk, they want to make sure that it follows the standard. So there are quick ways to do that. But in order to run these analyses, the machine needs to be calibrated with milk samples. And the way they do it, they actually create milk and with different composition of protein and fat. So you have the same kind of texture of the milk, but it has different proteins and different fat and different moisture and all of that. So they can use these samples to calibrate the machine. And they get the known concentrations of these standards by running Caldol, Moginer, oven methods for moisture and dry ashing for ash. So they have to do the official methods of analysis and then relate the concentration to the IR spectra. For fat, they will be measuring the bonds of carbonyl. For protein, the bonds of amide group. For lactose, it would be the hydroxyl groups is what would be the bonds that would be monitored for quantification. Most of the new instruments are really based on FTIR. And then they use multivariate regression equation to convert the complex spectra into concentration. So Raman spectroscopy, it's what I want to say here, it's a complementary method for determining or identification and structural characterization to mid-IR. So it is complementary because it measures the movement, the symmetrical. There is asymmetrical and symmetrical. The IR measure asymmetrical and Raman measures symmetrical. But anyway, they complement each other. But what happens in Raman spectroscopy, you have two types of scattering, one called Rayleigh scattering and Raman scattering of light. So what happens in IR, not UV, it's specific to IR. The light hits your molecule, it absorbs vibrational energy, and then some molecules release all of this energy as light when they go to the ground state. That's Rayleigh scattering, when all of the energy is released back as light. Raman scattering, there's a slight difference here where some molecules don't go back to their ground state. They go back to a higher vibrational state than the ground state and release energy that is less than of a wavelength that is larger and energy that is less than the energy that hit that molecule at the end, at the beginning. So that is Raman scattering, and that light that is scattered, which is of a lower energy than the incident beam, is what's measured. So that's the difference between these two, and it's a very, here's what I say, symmetrical versus asymmetrical, and it's a very unique tool and provide less complicated spectra than the IR, regular IR spectra, and provides valuable structural information. And it can be applied to solid and liquid, which is advantage because water does not have high signal in Raman, whereas it has very high signal in IR, regular IR. So it can mask other signals. So you don't have interference from water. So that's great. So you can measure solid and liquid samples or aqueous. And the source of radiation is infrared-based laser, so that you don't get interference from UV or fluorescence if you use a UV vis laser. Okay, So the intensity of the light scattered is specific to the frequency and proportional to the concentration of the molecules that cause the scattering of light. Okay, and IR is also very common. Near infrared spectroscopy is very common for composition of different types of food and mostly solid foods. And it's based on diffuse reflectance technique. And what that means, here's you have your sample, and usually it should be a ground powdered with homogeneous particle size. What happens is the light is going to hit that surface. Some of the light is going to be reflected without interference with your sample, and that is going to be reflected at the same angle that the light has hit. Other part of the light is going to go through the sample and excite some of the molecules, and some molecules will absorb light radiation, and the light that was not absorbed will be reflected at a particular angle, and that will be detected. So usually they have detectors at different locations to capture all of the light that gets reflected. So the light that gets reflected carries information, chemical information about what absorbed the light, basically. So, and here you also have, so you get chemical composition based on the compounds present in your sample that were able to absorb the light, and the remaining light was reflected. In IR, however, in near IR, you don't have sharp peaks like you have in mid-IR. So they're really broad peaks, so you have low sensitivity compared to mid-IR. And the detection is based on functional group that has a hydrogen atom. The hydrogen atom will be either linked to the carbon, nitrogen, or oxygen. So either OH in water, NH in protein, CH in lipids, OH in carbohydrate as well, and CH in carbohydrate. So these components, different components, they will have absorption of different functional groups. All of them are the ones that are attached to a hydrogen, and that would be the wavelength at which they absorb. This should be wave number, by the way. This is an error in their chapter. I just noticed that. I need to report the error. Okay. So here is an example of a cheese spectra, and here's an example of wheat and egg white. Notice here that you have this large peak here. It's due to the high moisture. So it kind of masks some of the protein kind of spectral. So it is a very complex spectra. Because of its being complex and masking, some peaks will mask other peaks. There's a lot of mathematics and calculation that goes into integration of this spectra. So the radiation source is a tungsten halogen lamp. You can use a quartz envelope. The quartz does not absorb light in the near infrared. It does absorb in the mid-IR. You can have a dispersive unit, or you can have also interferometer like you do in mid-IR. And you can use Fourier transform technology for the mathematics there, and you get rapid scanning and spectra simultaneously. Different types of detectors. You can have reflection. Mostly it is reflection when you have solid material, or you can have transmission if you have liquid samples. And the reflection is like I mentioned, and also in transmission it's regular like UV and vis transmission. And here, like I mentioned, you can do qualitative analysis and you can do quantitative analysis. With the quantitative analysis it involves quite a bit of complex mathematics because of the complexity of the spectra, but you can still calibrate with a set of independent samples that have been generated and analyzed using primary method of analysis, and you calibrate and you use regression and principal component analysis to convert spectra to concentration. So here's an example for applications. It is widely used near IR for grain, cereal products, oilseed processing, and some of these methods are actually AACC approved methods as long as calibration has been followed. And it's often used also for dairy products, butter, cheese, milk, whey. And we cannot emphasize enough on the importance of calibration. If the instrument is not calibrated, you're not getting good results. It's been used quite a bit for identification of contaminants, and this is a spectra, for example, near IR for how infant formula will look and how melamine will look. And if you have some of these peaks here, you can say, well, okay, then I have probably melamine in my sample. If they show up where they wouldn't have shown up otherwise if the infant formula does not have melamine. Just that I guess, so it is true. You can use that for online measurement. And then here's a list of advantages and disadvantages. I'm not going to go through them. I want you to just go read through them so that you know the differences between mid-IR and near-IR and the limitations associated. Wow, I finished 3 minutes early. Okay, but good. I hope you noticed when I slowed down. Okay, then, no, you did not? Oh, come on. You have to listen to the recording again. So, Friday, you have moisture with our esteemed Dr. Labuza. All right. Yeah. Oh, okay. Nicole, I have a very good question. The exam on Monday, is it on the material we covered up till now? You won't have moisture as part of the exam. Everything from the beginning of the semester, so not from the last quiz. Okay, so I will post the key of the exam 1 sample online. I will probably return your quizzes on Friday. Otherwise, I will put up the key of the last quiz you've taken. And I will put up key question for all the labs that you have submitted so far. And if you haven't noticed already, I focus a lot on lab. Okay.